When you set a wider spec range, it's also easier to achieve a higher CPK or sigma level. And to what extent can you interchange or compare these things? And why would you do it in the first place? Let's dive into this video to find out. Hello, I'm Tom. Welcome to my channel where we talk about continuous improvement in an industrial setting. And today's video is an answer to a question by Lucas on the channel and afterwards also by mail. Thank you, Lucas, for posing that question. And it is about a piece of CPK statistics that he found where the writer states that when you expect a higher sigma level or a higher CPK, you should not reasonably expect the spec limits to stay the same. In fact, they then go on to give a table of different sigma levels and the accompanying specification limits that would be basically comparable. So the same process. Now, that at first got me thinking, okay, yeah, well, this is a very statistical thingy. Why would you interchange those? But I think even that part is already very interesting to at least discuss, so that you see what this table means, but also that you see how the sigma level, the CPK level, how it interacts with how wide you make the specification limits. And the second thing is, so what is a good level, or at least how can you enter the discussion with a customer or a supplier, because usually these CPK levels, they are determined between a supplier and a customer of mostly industrial goods. And how can you discuss what a process does and what you can expect from your products that you're getting? The first thingy, and I'll just start with basically the same example that they use for giving most of what is in that table. And that is, let's say that we have a product where we have a specification and that it is so many millimeters plus or minus 100 micrometer on a CPK level of 1.33. So let me just write that down and then we'll get into the detail again. So what they say is we want a part with X, whatever, diameter or length, and the tolerance we allow around this specification is that it can be 100 micrometer smaller or larger. Okay, so we've got some tolerance, which is good because we know that you always have some natural variation in your process. And in this example, this type of specification, we also assume that you want to hit X dead in the center because they give an equal tolerance to both sides. This is not always the case, so be a bit mindful about that. But here we assume that they would like us to center the process, and what they then also say is how many of those pieces should fall within 100 more or less micrometers, and they do that by saying we expect a CPK of 1.33. And this translates, check my previous video, into 4 sigma levels. Now, what does that mean? When we have our natural variation, actually, let's first start with our specification line, the way our product works. We want our thingy to be centered around this minus 100 to this plus 100. And a CPK of 1.33 or 4 sigmas, that means that we have a distribution of our normally distributed variation in the process, in our component, of 1, 2, 3, 4 sigmas, 4 standard deviations between the center line and the specification limit, and the same also on the other side. So 4 times the standard deviation. Now that gives us 4 sigmas or a CPK of 1.33. Then they go on to say, now what would be a CPK of 1 and a CPK of 1.66 and a CPK of 2? And we've talked about this before. If you up or down that CPK, you are also, and I don't pick 1 and 1.66, 1.67 and 2 for nothing. This is directly translated in how many sigmas fit between the specification lines. So bear with me for a minute while I write some stuff down. Now, one of the first basic things is that a CPK of 1 is the same as having 3 sigmas between your mean and the specification limit. Usually, you first get a specification limit with a tolerance. So usually what this means is that you first get those red lines, then you measure your own process, your products coming out, and you say, okay, well, it's nicely centered in our ideal example, and the spread is so wide that we fit 3 standard deviations between the mean and the shortest of those 2 specification limits, the tolerance limits. Then we are talking about 3 sigmas, CPK of 1. Now the example that we used has 4 standard deviations, so that gives us a CPK of 1.33, 5 and 1.67, and 6 and 2.0. They are all equivalent. So if you have 6 standard deviations between the mean and the specification limit, then you have a process that has a CP or CPK of 2. For a CP of 2, it just needs to have a total of plus minus 6, so 12 standard deviations that fit between upper and lower. What we use generally is to say Cpk, so with this centering coefficient, and that means you pick the closest of the 2. But all those things, I'm skipping over it quite fast now. Go check my other videos online on that difference, CP, Cpk. These are basically coupled. Now, what does the author then go on to talk about? They say, so if you have this process, and we know that this is the process that our factory makes, right? So this is our baseline. So if we would make equivalent specs for that, if our supplier, if our customer really wants to have a CPK of 2, what should we give them as the tolerance that should fit with that? I'm a little bit at a loss of why specifically you would want to increase then suddenly the tolerance, because it sort of feels like cheating, although we will come back to it. There are some reasons why to do it, but first of all, let's talk about what it then means. In the table, what is given is for the CPK of 1.33 and a sigma of 4. This we get in our product when there is a tolerance, a specification tolerance of plus minus 100. Now, what they say is, if this is our process, an equivalent of that, so if we really want a CPK of 2, we should have 6 standard deviations between our specification limits. If we calculate this back a bit, we see that 100 divided by 4 is 25 micrometers. That is 1 standard deviation for this product coming out of our process. So they switch it around a little bit and say, if you want 6 sigma, then give us a specification tolerance of plus or minus 150 micrometers. And then you get a CPK of 2. Now, before we dive into is this really useful, let's dive in visually what this basically meant. And we'll only take the 6 sigma one here. It is with the red lines, we are on a CPK of 1.33. So if you take minus 150 plus 150 as specification limits, not changing the process at all. You see, right, the black line, our product coming out of our process, I haven't touched it. What I simply did is broaden the specification tolerance so that I can put 2 more standard deviations in on either side. And then we get to Cpk F2. That, Lucas, is what is in the table in your statistics book. And what it basically does is have a discussion of when you know that this is your process, well, this is your process, but your customer wants different CPK levels or different specification tolerances, without changing your own process, you can pick any of these equivalent levels. So you know that your factory, if you can make this, but your customer says, no, it has to be within 75 micrometers, then you can say, okay, well, we can do that, but we'll have a CPK of 1. So that means 99.7% is still in there, but a CPK of 1. And if they say, but we really demand a CPK of 2, then you say, okay, well, we can do that, give us a tolerance limit of plus minus 150. I also asked Paul Allen sort of to react already on this video. I hope, Paul, that you are watching this video when it's going live, and also now get a bit better feel of the actual question involved. And for the rest of you, if you're not following Paul Allen yet, do, because he has a very good grasp of Six Sigma, but also a lot of continuous improvement. And the one element where he is much stronger than I is in design for Six Sigma and design of experiments. Lately has been publishing a very nice set of videos also about design of experiment. And I'm hoping he will give another view on this, more from the mechanical industry and more from the between industry contracting, because that he has a lot more experience on. Now, what this can do for you is when you get into how do we design our processes, are we going to design a process that is going to give us a Six Sigma result, right? So design for Six Sigma, where and now we take the side of the customer of these parts. So we are going to check what is coming into our factory, and we design our process in such a way. So, okay, we want a very stable quality product to come out. Judging different suppliers, we see that with a very high trustability, so with a very high reliability on being within those specifications, they can supply us with parts that have a variation in tolerance of plus or minus 150 micrometers. So if we can make the rest of our process fit to whatever we get within plus or minus 150 micrometers, and this does not seriously affect things that we are doing to the rest of our product later in assembly, or maybe to how our equipment behaves, and our processes can simply handle this tolerance around the specification, then we know that this part of our process and product will give us a very high stability within that. So if we compare, we might say, oh, well, maybe there are specs on the market that have a lower tolerance, but that is not per se what we're looking for. Then we are looking for a setting, or in this case, an ingredient, a part that we buy from outside or make within our own manufacturing somewhere, that can always deliver on a specific set. So always deliver on our average plus or minus a certain tolerance, right? So, and in this case, the tolerance we need to design with when we are planning the rest of our production process is that this part will have the plus or minus 150, and then we know that if plus or minus 150 doesn't really matter to our process, we have a very stable part here that we don't need to worry about. Now, that is how you can use it in designing and in checking what your customer needs to deliver, but also in more making designing the process and designing the settings for your machines, but also the tolerance of other parts that you put in, and making sure that you are basically never running into trouble. Because if you design a process where this part can only have about 75 micrometers of tolerance, and as soon as it gets outside of that limit, you will see that it jams into a machine, or it doesn't fully fit into the next part, the container part. At that moment, you know that, okay, CPK 1, 3 sigma levels, that will give us a mistake, a problem, at least a couple times every 1,000 parts. And if we're in a high volume manufacturing organization, several times every 1,000 parts will happen, maybe daily. So that will give us a relatively low reliability. So when we are designing for Six Sigma, we need to make sure that we can handle the tolerance that fits with 6 sigma of variation observed in each part. Apart from that, as I said, I mean, this table does not improve your product. It is useful sometimes for discussing specifically how we should design our process, but as it is printed in that statistics textbook, it's basically more of a discussion on what is equivalent. So how can I compare tolerance limits to the known standard deviation, because we know here from this example process that the standard deviation is 25, and how do you translate it into standard deviation or sigma level, and how do you translate that into CPK, and how can we make this a language to speak between supplier and customer, and maybe technology quality departments. So I hope, Lucas, that helped to clarify definitely the table. I'm sorry I couldn't give a very strong answer on why specifically you need it. As said, I hope maybe Paul can shed some light on it. Also, if we've got other people in our community, I mean, these are the things we work with quite frequently. So if one of you has a very clear reason why you go for a specific level without changing the actual process, do share it. I would be very interested to know. I'm sure Lucas would be interested to know, and the rest of the community as well. Now, if you like the video, don't forget to hit that like button. And as you see, I love your comments, your questions, make videos about them. So do keep feeding me with such feedback. It's greatly appreciated. For now, I wish you the best of luck in your Six Sigma journey. And as always, don't forget to enjoy that journey.